Hi everybody, this is my review for the APPM 2360 Differential Equations and Linear Algebra Final Exam. Now, given that I'm tired as hell, falling sick, and also in the middle of finals, rather than doing a comprehensive exam, I will only be discussing new concepts introduced since Exam 3. So new concepts for finals. Okay. Let's get started talking about Laplace transforms. I know that we went over this in probably in Exam 3, but there are three new functions introduced that'll be that could potentially come up on the final. And any Laplace questions that do come up on the final, you will be provided a table. Okay, so the three functions are the step function, it's a step of t minus a, the Dirac delta, delta of t, and the chopper function. The step function, step of t minus a, has a graph that looks a little bit like this. This will be our t-axis, this will be our output y. So this will be 0, and we'll set 1 to be up here. At a certain point, until a certain point a, our function will be 0, and then it'll discontinuously jump to 1, excuse me, and continue off that way. Defining this mathematically, we say that step of t minus a is equal to 0 for all t less than a, and 1 for t greater than or equal to a. The important thing that I note about this, it's just to have familiarity. If you see anything with an e to the negative as, it likely was due to a step function. So the Laplace transform of step of t minus a is equal to e to the negative as over s. Okay, next function, the Dirac delta. The funny thing about the Dirac delta is that it's not actually a function, it's what we call a functional. And that's because rather than if you notice, we don't define the Dirac delta using an algebraic equation like with everything else. We use a definition. So it is 0 everywhere on its domain, except for at x equals 0, or t equals 0, where it jumps up to infinity. And if we look at the mathematical definition of the Dirac delta, it's a two-part definition that, 1, it's 0 for all t not equal 0, and at t equals 0, it's defined by the limit as h goes to 0 of 1 over h. The other condition to produce the Dirac delta function is that the integral from negative infinity to infinity, basically the entire domain of the Dirac delta function dt, is equal to 1. Okay, next let's talk about, let me also move this up a little bit. Okay, next we want to talk about the chopper function. So the chopper function is actually a really clever combination of two step functions, and you can see why. If we plot out, this will be our t, this will be our y. If we plot out step of t minus a, that'll look a little something like this. This will be 1, we'll jump up here, b, continue on till infinity there. Okay, great. Now what if I subtract from this step of t minus b? Let me do this in purple actually. This step of t minus b looks a little bit like this. At b, my function, until b, my function will be at 0. At b, it'll discontinuously jump up to 1 and continue there forever. Excuse me. So now let's look at all these portions. Over here, 0 minus 0 is still 0, so our end function will just end up looking like a straight line. In this region here, again, my step t minus b is at 0, my step t minus a is at 1. 1 minus 0 means that this function will stay at 1. And then for the remainder of it, where step of t minus b is at 1 and step of t minus a is at 1, 1 minus 1 is equal to 0. So this will only be at 1 in between these two values in between a and b. And so mathematically, we define step t minus a minus step t minus b as being 0 for t less than a, 1 for t in between a inclusive and less than b, and 0 for t greater than or equal to b. Okay, and let's move on to talking a little bit more about eigenstuff. Okay. Eigenstuff. So eigenvectors and eigenvalues. How do we find eigenvalues? So we find these eigenvalues using what we call the characteristic polynomial, which is calculated using the equation your matrix A minus lambda I is equal to 0. And so this is called the characteristic polynomial. And what you can do is you can factor out all your eigenvalues. So factor out your individual eigenvalues, which I'll denote as lambda sub I. For each eigenvalue that you find, so for each lambda I, you can find your corresponding vector, eigenvector. So find corresponding eigenvector v sub I using the following equation: A minus lambda I times the identity matrix I times that vector v sub I is equal to 0. And it's important to note here that this matrix A needs to be in reduced row echelon form. So you need to have at least one row of zeros. Okay, let's move on to talking a little bit about systems of differential equations and their stability. So let me also move this up a little bit. Move this over. Oh, Christ. Okay. So systems, systems of differential equations and their stability. So we can represent a system of differential equations as a matrix equation. So we can represent as x prime vector is equal to the matrix A times the vector x. And for a 2x2 system, we have a nice formula for our eigenvalues, where lambda is equal to the trace of A plus or minus the trace of A squared minus 4 times the determinant of A square root all over 2. And you may recall this from the quadratic formula. It's just the factoring of the characteristic polynomial. Just a little bit of a notation thing. So this stuff inside the square root, this is what we call delta, or the discriminant. And so delta is equal to, that's really ugly, delta is equal to trace of A squared minus 4 times the determinant of A. And so there's 3 situations that you're going to have to deal with. First is if your discriminant is positive, when you'll have real and distinct eigenvalues, so lambda 1 and lambda 2. Next, if you have a negative discriminant, then you have complex conjugate lambda 1 and lambda 2 given, and that means that, excuse me, Christ. So lambda 1 and lambda 2 are going to be equal to alpha plus or minus beta I, like every other complex number, where alpha in this case is the trace of A over 2. Beta is just the square root of the negative discriminant. It's just this, once again. And then the last case is if your discriminant, delta, is equal to 0. Okay, if you have a positive discriminant and you have your 2 real distinct lambda 1, lambda 2, there's 2 scenarios. So you could have both your eigenvalues, lambda 1 and lambda 2, both negative, and this will be an attracting node. If you have your lambda 1 and lambda 2 both positive, then you'll have a repelling node. And if you have one eigenvalue negative, one eigenvalue positive, then what you're going to have is a saddle. Here the choice of lambda 1 and lambda 2 is completely arbitrary. As long as you have the signs being both negative, both positive, or mixed signs, that's what determines the behavior. Okay, if I have my complex conjugate roots, my behavior to the system is determined by my value of alpha. If my alpha, so the real part of my root, is less than 0, I'll have an attracting spiral. If my alpha is positive, then I'll have a repelling spiral. And if my alpha is equal to 0, then I'll be at a center point. The last cases that I want to consider is if your discriminant is equal to 0. There are two interesting cases here. So you're going to only have one eigenvalue, but this could lead to either one linearly independent vector, or two linearly independent eigenvectors. And just a note that the symbol in my notation means independent, because that takes a long time to write. So in this case, you'll have a degenerate node, and if you have two, then you'll have a star node. And the way that these look, for a star node, you have all your trajectories pointing out. For a degenerate node, it'll probably look something a little like that. If you want to see good examples of either of those cases, there's section 6.2, examples 5 and 6 are a good one for the one linearly independent vector, and then section 6.2, examples 4 are good for the second case. Now, I made this image beforehand, so I'm just going to copy and paste it in because I don't feel like drawing the whole parabola plane out, but now we're going to discuss the trace determinant plane a little bit and discuss what that means for the stability of your system of differential equations. Okay, let me just rearrange this. Okay, perfect. So if I'm underneath, excuse me, so this line out that I have out here is defined as a point where of the points of trace A and determinative A where my discriminant is equal to 0. Beneath this, I will have attracting nodes if my eigenvalues are negative. I have repelling nodes if my eigenvalues are positive. If I'm on the line, that's the case of the repeated eigenvalue, so I'll have a degenerate node. That's this one here. If I'm on the left side of the positive discriminant axis on top of the parabola, then I'll have an attracting spiral where it goes in like that. If I'm on the left side, then I'll have a repelling spiral, so it'll go out like that instead. Inside this parabola region, both of my eigenvalues are given as my complex variables. So it'll be alpha plus beta I, where alpha is equal to the trace of A over 2, beta is equal to the negative discriminant, or negative square root of the discriminant. These are the regions that my system will be in if depending on my value of alpha. This entire axis is given by all the traces where at least one of your eigenvalues is 0. And then below this trace axis, you'll have a saddle where both of your eigenvalues have opposite signs. Let's move into talking about stability, specifically with our friend, the simple harmonic oscillator. So stability and the simple harmonic oscillator mx double dot plus bx dot plus kx is equal to 0. So if you recall from our study of the simple harmonic oscillator earlier, if b is equal to 0, this is what we call undamped. If b is between 0 and the square root of 4mk, and this is underdamped. If b is exactly equal to the square root of 4mk, this is critically damped. And if b is greater than square root of 4mk, then this is overdamped. And specifically because we have this well-defined equation, I think it's worth knowing, or at least having familiarity with what the end solution is without having to derive it each time. So your eigenvalues, lambda 1 and lambda 2, are going to be given by negative b over 2m plus or minus 1 over 2m times the square root of b squared minus 4mk. Cool. If we take a look at the phase plane, let me just move this here, actually, yeah. if we take a look at the phase plane of a simple harmonic oscillator, this will be our trace of A axis, this will be our determinant of A. So my center will be my undamped systems. If I have an underdamped system, I'll have, or let me just write this out. So center, undamped. If I have an attracting spiral, or that's the wrong way. If I have an attracting spiral, this is underdamped. This will be my parabola. This will be degenerate nodes. So critical damped. And that'll look a little bit like if I have my lines going out, that's the wrong way. If I have my lines going out like this, just going in like that. And you should know that these are curving around. They're not going straight in. They're curving in the way that degenerate nodes do. Christ, I just had a stroke. And then my last situation is if I have an attracting node. Where it'll look, this is where all the points will start to come in. And the way you can graph this, remember, is just by picking a couple points in your plane and seeing the way the trajectories lead you. Okay, now let's talk more about solving systems of differential equations. So, systems of differential equations. These are equations representing the form that x prime vector is equal to a times vector x. And we can get solutions to what our x is using e to the lambda t times our vector. And this will be a solution if and only if lambda and v are eigenthings of A. Essentially, that they solve this equation, A minus lambda I times vector V is equal to the zero vector. So let's discuss our three cases here where we could have distinct real eigenvalues. So distinct, real lambda 1 and lambda 2 with associated eigenvectors v1 and v2. And here solutions will be e to the lambda t, or lambda 1t times v1 plus e to the lambda 2t v2. And expanding this out into your proper solution, you're going to have to remember to add constants in front of it, but your final solution, x vector of t, will be c1 e to the lambda t, e to the lambda 1t times v1 plus c2 e to the lambda 2t times v2. From this, you can draw out your phase portrait. So, phase portrait. The important thing, the steps to take when drawing your phase portrait is first draw your trajectories along eigenvectors, because trajectories along eigenvectors are straight lines. And then you also know that the speed at which you're changing is proportional to your eigenvalue. So speed is proportional to eigenvalues. If you have, if you're taking a look at your fast eigenvectors, so trajectories become parallel to fast eigenvectors or tangent to them. And they do this further from the origin, further from the origin. If you have trajectories that become tangent, trajectories that become tangent to closer to the origin are caused by slow eigenvectors. So trajectories The last thing that we'll say is that positive eigenvalues lead to trajectories that move out. And negative eigenvalues lead to trajectories that move in. Okay, we also have the case of repeated eigenvalues. So, repeated eigenvalues. So, find your one eigenvalue and your one distinct eigenvector. And so to do so, you're going to find a non-zero vector u such that the equation a minus lambda I times u is equal to your vector v. From this, your solution will be given by x vector of t is equal to c1 e to the lambda t v plus c2 e to the lambda t times vector v plus u. So for non-real eigenvalues, this is where your lambda 1 and lambda 2 are given by alpha plus or minus I beta, where alpha is equal to the trace of a over 2, once again, and beta is equal to the negative discriminant over 2. Oh, crap. Sorry, I forgot earlier up here it should be beta is equal to negative discriminant over 2. My bad. Here, you will have, for each lambda I, you want to find your vector v given by p plus iq, where once you have those two vectors with real and imaginary parts, you can solve out for your real solution, so xre, which is given by e to the alpha t cosine of beta t times your vector p minus sine of beta t times your vector q, and your imaginary x is given by e to the alpha t times sine of beta t times p plus cosine of beta t times q. And thus your final solution becomes x vector of t is equal to c1 times your real solution xre plus some other constant c2 times your xim. Okay, I think that's it. Best luck on the exam. I'm sorry this is so late. You guys got this.